This is the second in a series of data warehousing video-based lessons that will introduce the basics of dimensional modeling, aka Inmun's data warehouse design. We will discuss the reasons why this type of data model became the industry standard, and will dissect its two main components, dimensions and facts, in some detail. The two main reasons dimensional modeling is the data warehousing industry standard is the simplicity of design and speed of query performance. Dimensional model can be easily visualized with an aid of an all-up cube, such as the one shown in the top right corner of the slide here. Each of the cube elements represents the total sales for a given product in a given store and in a given month. So the bottom right and front cube piece represents the total April sales for product number 3, I think that's what this reads, okay, and in store number 4. This makes it very easy for an average business user to understand and relate to. In addition, the relatively few direct joins between dimensions, store, month, and product, and measurement facts like sales, so 3 in all for this example, make for a relatively fast query execution even when accessing millions of rows. That's the relative piece, I guess. As was already discussed in a previous presentation and videos, operational systems are fully normalized 3NF or third normal form structures that are designed to optimally process day-to-day operational transactions affecting few rows at a time. These systems are simply not designed to run complex queries affecting millions of rows. Aside from the slow performance of those queries for BI users, they degrade the performance of the operational system needed for smooth daily operations of the business. On this slide, we introduce our running case example, a student registration or enrollment operational system, a spaghetti cobweb of entities and relationships, shown here on the left slide, designed for efficient processing of student registration/enrollment requests. Some of the transactions include student adding or dropping a class, changing to another section, or requesting to be placed on a waiting list for a section that is full. All these examples are examples of insert, delete, and update queries affecting at most few rows at a time. This system is not designed with open-ended BI queries such as finding the total enrollment for Introduction to Finance class in spring 2029 semester and then comparing that enrollment with enrollments over the previous five periods for the same, or terms I should say, for the same class. Another way of thinking about the dimensional model is to view it as a denormalized analytical system, completely separated from the operational system. We will discuss the degree of normalization a little bit later on when we compare star and snowflake dimensional modeling schemas, but these denormalized structures are ideal for fast querying of millions of rows because of the minimal number of joins, which is a direct result of denormalization. Whether the implementation is that of a star schema in an RDBMS or an all-up cube, like the one again in the top right corner, the logic of using a few measurement facts, typically a single one like sales, surrounded with several dimensions such as these 3 shown here, store, month, and product, is the same. It will result in a similar fast query performance, even faster with all-up cubes, which is the key to all DWBI analytical systems. Continuing our student enrollment example, the current slide represents one relatively simple dimensional model with an enrollment fact table surrounded with several dimensions. Okay, right here. We will study the fact table and each of the dimensions in detail as an in-class project, but want to simply show right now the simplicity and elegance of this particular dimensional model. Just a cursory visual examination of this model shows that enrollments, right here, and grades are the fact measurements we can summarize across multiple dimensions from terms, semesters, students, courses, faculty, dates and times, and locations. Okay, so finding the enrollment for all sections of Introduction to Finance course over multiple terms needs the course key here from the course dimension to identify that Intro to Finance class, the term key from the term dimension that's going to identify then spring of 2029, and one measurement, the enrollment, from the fact table itself. Okay, a simple query with only these two joins, this one and this one, the has between term dimension and enroll fact, and offers between course dimension and enroll fact will do the trick. Multiple day, time, dimension key values for the same Intro to Finance class and the same term would represent the different sections of the class in the current model setup, although this could be differently in a different model. For a more in-depth study of student enrollment in other university or education, I should say, related dimensional models, please see Kimball's book, Chapter 13. And this is a good place to pause.